In the last video, we defined two well-formed formulas to be logically equivalent if and only if they have the same truth value under every truth assignment. In this video, we're going to look at some useful examples of logical equivalences that are helpful to us, for example, when we want to prove things. So let's begin with double negation. The theorem that we've got here says that if you have a well-formed formula phi, then phi is logically equivalent to not phi. So to prove that, what I have to do is to show that for any truth assignment at all, phi and not phi have the same truth value. But we don't know which variables belong to phi. It could have one variable, it could have lots of propositional variables in it. So I can't do this just by drawing up a truth table for every propositional variable inside phi. Instead, what we can do is to say that under any truth assignment, phi must be either true or false. So we'll just look in both of those cases at what truth value not phi gets. Now, if you remember, our way of assigning truth values to well-formed formulas under a particular truth assignment had a particular property. So one property is that if the truth assignment is called V, then V of the negation of any well-formed formula is the same as the negation of V of that well-formed formula, like this. So when phi is true under a particular truth assignment, then V of not phi would be not true, which is false. So I can put a false here, and similarly I can put a true here, just doing the same argument again with not phi in place of phi. Okay, on the same kind of argument shows me this time if phi is false, then not phi would be true and not phi would be false. And what you can see here is that this column is the same as this column. Therefore, under any truth assignment, phi and not phi get the same truth value. And this method is actually a very useful one for doing logical equivalences, for proving that a particular logical equivalence is true. You can look at all the possible truth values that the formulas involved could take and check that under each of those possibilities, the two formulas you want to be logically equivalent get the same truth value. Let's look at another example of that. So here are De Morgan's laws in logic. I say in logic because we're going to revisit De Morgan's laws when we study set theory. So De Morgan's laws are about two well-formed formulas phi and psi, and they say that the negation of, so not phi or psi, is logically equivalent to not phi and not psi, and the second one says that not phi and psi is logically equivalent to not phi or not psi. So again, to do a proof of this, we can observe that under any truth assignment, phi is either true or false, and psi is either true or false. So we'll just look at the four different possibilities and check that in each of those four cases, the truth value of this thing is the same as the truth value of this thing. And that means, if it's true, that they have the same truth value under every truth assignment, and therefore they're logically equivalent. So to check this, we just have to do some calculations. So let's begin with calculating the value that's going to appear here. So in this case, we have phi and psi both being true under our truth assignment. So the truth value of not phi or psi will be not true or true. So from the truth table for not true or true is true. So this is not true, which is false. So I should put a false here. So let's just join this up to where the calculation happened. And let's do the other column in that row. So for this entry here, let's work it out. Phi and psi are both true under this truth assignment. So the truth value that goes here is not true and not true, which is false and false. And from the truth table for not, that is false. So I'm putting a false here. You can see that the truth value for both of those formulas was the same, and so nothing bad's happened yet. So we just need to keep going now and do the other 3 rows and check that we get the same truth value for not phi or psi as we do for not phi and not psi. So let's do the next one at least. We're going to do this one here first of all. So let's join it up to where the calculation's going to be. It's going to be here. This time phi is true and psi is false under the truth assignment we're thinking about. So we're looking at the negation of true or false. Now from the truth table for or, true or false is true, so we've got not true, which is false. So here we put false, and if we look at this one here under the same class of truth assignments, we now have not true and not false, since phi is true and psi is false under this truth assignment that we're thinking about. So this is false and true, and by the truth table for and, that is false. So we put a false here, okay, and you can now keep going and check that in the other 2 cases as well, you will get the same truth value in both of those last 2 columns, and therefore those 2 formulas are logically equivalent. So that proves part 1. If you complete this set of calculations, you have proved the part 1 of De Morgan's laws, and part 2 can be done exactly the same way. So I'd like to mention an important generalization of De Morgan's laws, which is a generalization to when there are more than 2 formulas. So it's in fact true that if you have any well-formed formulas phi 1 up to phi n, then the negation of phi 1 or phi 2 or phi 3 up to phi n is logically equivalent to not phi 1 and not phi 2 and not phi 3 all the way up to not phi n, and the same with not and or swapped over. Now you might object that what I've written here, for example, is not a well-formed formula, and you're correct, that's not a well-formed formula. But because or is associative, because logical or is associative, any of the ways to which we can add brackets to that formula to make it into a well-formed formula is logically equivalent. So we can regard phi 1 or phi 2 or up to phi n as being, or referring to, any of the well-formed formulas you can get by adding brackets. And it doesn't matter which one, because by the associativity property for or, they're all logically equivalent. So they all have the same truth value under any truth assignment. Okay, and of course we do the similar thing for this part, which again is not a well-formed formula, but any 2 ways in which you add brackets to this to make it a well-formed formula result in logically equivalent well-formed formulas. Final couple of logical equivalences then are the distributive laws. So you might have heard of the distributive laws in arithmetic. So people say that multiplication distributes over addition to mean that a multiplied into b plus c equals a times b plus a times c. And the distributive laws in logic say the same thing, only instead of multiplication and addition, you have and or and. So one says that phi and psi or theta is logically equivalent to phi and psi or phi and theta. So that says that and distributes over or, and part 2 says that or distributes over and. Now, I'm not going to write down the proofs for these. You can do them just by working out the truth tables. And of course, these truth tables have got 3 well-formed formulas in them, so they'll have 8 different rows. It's good practice to do this yourself, and you can check the answers in the online notes where I have calculated the truth tables in full.